Okay, so our lesson today will be looking at describing the intersection between two planes. I know I have 3 planes written right here, but I'm going to do that in part 2. So part 1 is going to be looking at what happens when we have 2 planes and they intersect, and how to be able to recognize those situations. Okay, so here's a diagram of 3 different cases. So these are the 3 different things that can happen. I'm going to start with the case 3. So in case 3, if we look at it, it looks like there's only one plane. And that's because the equations are scalar multiples. So the normals are the same and the multiples and the d values are the same. When we're going to be doing these questions with the intersection of planes, we're going to use the scalar format because it's easier to work with. So they're scalar multiples. So they're exactly the same plane. So we call this coincident because every single point on one plane is a point on the other plane. So this here would be considered infinite solutions. Now case 2, the normals are multiples. But the d value is not. So we say that this here is no solution. And the one that requires the most work is if the normals are not multiples. So there's an intersection that occurs. Now, in this diagram, it looks like they're perpendicular. They can be perpendicular, but they do not need to be perpendicular. So as long as they're crossing each other, we're always going to end up with a line of intersection with 2 planes. That's the only possibility. We can't get a point. We can only get a line. So if you picture where 2 walls meet, that corner, that whole line representing that corner that you could draw, that would represent the line of intersection. So here, normals are not multiples. So all of these questions, and today we're focusing on 2 planes, however, even 3 planes, our very first step is to look at the normals. That gives us the possibilities that we are looking for. Okay, so actually let's get to the examples. All right, describe how the planes in each pair intersect. So when I'm looking at this expression, so I see normal 1 is 2, negative 1, 1. Normal 2 is 1, 1, 1. So that means these lines intersect, or sorry, these planes intersect at a line. So what do we do? So this is a process. So once you know how to do this, this process is never going to change. So we're going to start by, step 1, we're going to eliminate a variable. Okay, so I'm going to choose a variable to eliminate. It's up to you which one you want to eliminate. Sometimes one variable is easier than another, and in this case, I'm choosing to eliminate z. So if I'm going to eliminate z, I'm going to subtract these equations. So I have 2x subtract x gives me x. Negative y subtract y gives me negative 2y. And z subtract z goes away. That's what I wanted to happen. And I have negative 1 minus negative 6. So that becomes negative 1 plus 6. So I have plus 5 equals 0. So this here is a representation of our line. But it doesn't look like the equation. Well, actually, this one does look like the equation of a line. However, it is not. I need to create parametric equations. So I'm arbitrarily going to say, let y equal t. So I'm forcing this to be one of my parametric equations. So let y equal t. A line has 3 parametric equations. We have an x, a y, and a z variable. So I need to generate those equations. The next one I can get is x. So I'm going to sub y equals t. So I'm going to cut into this equation. So I'm going to have x minus 2t plus 5 equals 0. So x equals 5 plus 2t. So that is my x parametric equation. So I'm just going to add a little note here. So y equals t into the new equation. Okay, so I got y, I got x. That means I have to get z. So in order to get z, we are going to sub y equals t and x equals 5 plus 2t into the first or second equation. I'm going to go with the second one because there's fewer coefficients, so it just makes it easier to work with. So I have x plus t. Oh, I need to go back because I know what x is. So I have 5 plus 2t plus t plus z, and I'm going to move that 6 over right away. So when I do that, I'm going to have z equals 6 minus 5 is 1 minus 3t. So this here represents the parametric equations for the vector equation of the line of intersection. So now I'm going to write that as a vector equation. So from the parametrics, when I look at the x, the position vector that I have is 5, 1, and 1. And I have plus t. My direction vector, so the x value is 2 because that's the number with the t. My y is 1, and my z is -3. All right, now I just made another little mistake. So that position vector, the y, it's not 1. Because when I look at this equation right here, this is y equals 0 plus 1t, not 1. That would change things dramatically. Okay, so that represents the vector equation of our line. So generally speaking, two planes, as long as the normals are not the same, this is always going to happen. Now, depending on what value you pick right here for your parameter, everybody might get a different position vector. However, what will be the same for everybody is the direction vector will be the same. And by the same, I mean it can be a multiple, but it has to be the same because a line has a unique direction vector. All right, next example. Okay, so if we're looking at these two equations, I'm looking at my normal. So my normal equals 2, -6, and 4. This normal equals 3, -9, and 6. So when I'm looking at that, I'm like, okay, so these numbers, they look kind of similar. So if you want to see if they're multiples of each other, you could easily take one number and divide it by the other and see if you get the same value to see that there's a scalar multiple. So if I do 3 over 2, I have -9 over -6, which reduces to 3 over 2. And then I have 6 over 4, which also gives me 3 over 2. So the normals are multiples. So now I'm going to look at my d values. So d is -7, d is -2. So -2 over -7, not 3 over 2. So therefore, these are parallel planes. Therefore, no solution. They'll never cross each other. So their normals are the same, but the d values are not the same. Okay, so the next scenario. All right, so once again, we have normals. So another way that you can show this is if you recognize that they might be multiples of each other, I'm going to go ahead and I'm going to multiply by 2. So when I multiply this equation by 2, and I'm allowed to do that, as long as you apply it to everything, what do you notice? They're the exact same plane. So therefore, the planes are coincident, infinite solutions. Okay, so not only are the normals multiple, but the d values are multiples as well. Okay, so I'm actually going to stop here. So that's part 1, and then the next video will be part 2.